So we ended last time, we were talking about the 5 types of chemical reactions and kind of the difference between each of them. So we talked about um, combination reactions, decomposition reactions, the 2 different types of replacement reactions. And then what we wanted to start with today were the combustion reactions, the ones where we have oxidation taking place, where we have something that is reacting with oxygen. That's the real key and important part here. If we look at the reactants for combustion reactions, we always see oxygen gas, O2, as a reactant. And that oxygen gas is going to insert itself into the compound that it's reacting with. So we get carbon dioxide and water, then we have carbon and hydrogen products, and we can get other oxides when we have non-carbon products. So in the case of ammonia here, the nitrogen will react with oxygen, in this case to make nitrogen monoxide. And we'll get water as well because the hydrogen is still going to make that water product. But this is not the only kind of oxidation that exists. So when we think oxidation reaction, we usually do think about oxygen. After all, that is what oxidation is. Oxidation was named as such because it involved the reaction of oxygen with other things. Now there's a whole other class of reactions that kind of has its own thing. We call them oxidation-reduction reactions, sometimes known as redox reactions for short. Now, redox reactions are based upon the concept and the idea that there are these 2 processes that occur simultaneously. Oxidation, where we see elements and compounds either gaining high oxygen or losing hydrogen. But most generically, we talk about something that is losing electrons. So oxidation processes can occur a lot of different ways. Those are the 3 ways that we can spot it. If there is oxygen involved, we can use the oxygen to spot the oxidation. If there is hydrogen involved, we can use the hydrogen to spot the oxidation. But most commonly, this is the common trait for all oxidation processes, we're seeing losses of electrons. And so if we look back on some of the other chemical reaction types that we covered on Friday, what we'll see is that this process of oxidation is a key component of most of them. So redox reactions are kind of like an umbrella statement. It's not just one type of reaction or another, it's a whole class of reactions that include these subcategories. In fact, the one that we talked about that doesn't apply is the double replacement. In the double replacement reaction, because all that's happening there is that the ions are just switching places with each other, none of them ever change their charge. And so since none of them change their charge, none of the electrons are moving. That's the only one where we don't see some kind of charge change. If I look back, combustion reactions, yes, there's a direct oxidation involved here. The oxygen is inserting itself into that carbon compound. In these reactions, We don't always see it quite that way, but if you look closely, you can see that the magnesium went from having nothing to having a charge. So there was no charge on this magnesium. There's now a positive 2 charge on that magnesium. And the nickel went from having a positive 2 charge, no charge. So somewhere along the line, there were electrons that were exchanged in that reaction. Now we can follow it also by tracking the oxygen in that nitrate. The magnesium gained nitrate, gained oxygen, the sign of oxidation. In our decomposition reactions, you can see similar kinds of things. In these decomposition reactions, we are usually looking at substances that are either gaining or losing oxygen. So for example, the water here, the hydrogen has lost oxygen. The oxygen has lost hydrogen, so we actually talk about the oxygen being oxidized here. In magnesium carbonate, we see that the magnesium did not have an oxygen before. The oxygens were all with the carbon here. Now the magnesium does have an oxygen. It got oxidized in the process there. Combination reactions, not always exactly the same thing. But again, if you look at it from a charge standpoint, elements have no charge. That's what makes them elements. To form this compound, hydrogen's in group 1, so it's a positive 1 charge. Chlorine's in group 7, so it's a negative 1 charge. There are charges here where there were none before. So what we get into with these kinds of reactions, again, double replacement being the exception, because in double replacement reactions, none of the charges are actually changing at all. But we're seeing the movement of electrons, and we're often seeing the movement of oxygen or hydrogen, or both in some cases. Now, oxidation has a process that is paired with it. We call it reduction. You cannot have an oxidation without a reduction, because if oxidation is that loss of electrons, those electrons leaving something, those electrons have to have a place to go. And so ultimately, we're looking at this third one right here. When we gain electrons, we tend to see reduction. So oxidation has the loss of electrons, reduction has the gain of electrons. Now, what are some other things that we can look for to kind of help us figure that out? Well, again, dealing with oxygen and hydrogen is basically the opposite process. If something loses oxygen, then it's being reduced. If something gains hydrogen, then it's being reduced. If electrons are gained, then we're talking about reduction. So that's what we need to kind of focus on when we look at this broader class of materials. Again, it's not just one little thing. And oxidation-reduction reactions go far beyond combination, decomposition, single replacement, and combustion. There is a whole mess of reactions that take place that are oxidation reduction that don't fall into one of those 4 categories. But the thing that they have in common is that those electrons are moving in that chemical reaction. And actually, that movement of electrons can actually be advantageous to us. because that's basically what happens when we make a battery. When we make a battery, we're basically taking a chemical reaction, an oxidation coupled with a reduction, to get those electrons moving as the two reactions react. That movement of charge we can draw, and that becomes our electrical current. Now, in redox reactions, there are a couple of names that get put onto things. You can refer to substances that are oxidized as reducing agents. You can refer to substances that are reduced as oxidizing agents or oxidizers. And obviously, this last term has some significance for us because, after all, that is the very essence of one of the things that we have to look at as far as hazardous materials go. So when we get into talking about oxidizers, and this is not actually a place where we're going to talk about oxidizers as a class of compounds yet. But understand that those oxidizers, their primary focus has everything to do with fire and their ability to fuel and feed a fire. And now we have a little bit more of a context for why, knowing that the oxidizer is a key component of a lot of different reactions, not just combustion reactions. But when it is a combustion reaction, we know that the products of that reaction are usually going to be considerable gas, heat, and light. And all three of those things have their own inherent dangers, especially the gas and the heat. So we need to move now to balancing equations. Now, the reason we balance equations, we got into this just a little bit on Friday, has to do with a couple of things. One of them is something called the law of conservation of mass. Law of conservation of mass says that mass cannot be created or destroyed in a chemical process. It's simply just converted from one substance to another. Easy way to kind of check that for ourselves is when we do a chemical reaction, we do it in a closed container. We weigh everything before the reaction. We weigh everything after the reaction takes place. And the two values should be essentially the same. We also have to adhere to something called the law of conservation of matter. Law of conservation of matter says that atoms of any element can't be created or destroyed. Again, the idea is just rearranging. And then finally, the law of conservation of energy. Law of conservation of energy says that energy cannot be created or destroyed in a chemical reaction, just merely converted from one side to the other. And so you may ask yourself, well, if that's the case, why do we see changes in temperature associated with chemical reactions? Why does a fire feel hot if there's no change in energy? Again, it comes down to what the energy is. That thermal energy you're experiencing when something is on fire is the result of the breakdown of the chemical bonds that were in the substance that is burning. As that substance is burning, the heat generated by that reaction is causing those chemical bonds to break. And as those chemical bonds break, that actually requires energy to start. That's why you see that part of fire inside if you have wood. You can use fire starter of some kind to bring the energy in to help break those chemical bonds inside of that log. But once you do, the resulting product, carbon dioxide, the water, as those two compounds form, you will solve the energy all there that was kind of locked up. And that locked up energy release is significantly higher than the amount of energy that you had to put into the fire starter in the first place. And that's why the reaction continues to grow. That's why it continues to get hotter, because the end product has less energy than the start of the reaction. Less energy in the product, and we use that gas. And that's why we feel the heat energy coming off of that fire. So, law of conservation of energy tells us there's a conversion that's going to take place. Sometimes the conversion is going to be what we call endothermic, where we start with reactions that are relatively low in it, and we end up higher in energy, and using that endothermic to put in energy to get the product up high enough. Well, that energy has to come from somewhere. It comes from the surroundings. It comes from you. You feel colder as a result. That is, you feel away from the area around you. But in the opposite case, like in a combustion reaction, you have to have a higher energy product. You feel that heat energy. That's called an exothermic process. So to adhere to the law of conservation of mass, we need to make sure that we have an equal number of atoms for each of the elements on each side of our chemical equation. And we do so not by changing the chemical formulas themselves, because that would change the chemical identity, and therefore all of its properties, but instead we use coefficients in front of our molecules to help us get that balance. Now, this is a process that takes some time to go through. And so we're going to go through several examples today. And if you go into Blackboard, you'll see that in Blackboard, I've put extra practice problems and some more guided walkthroughs that you can go into to help you get good at this particular practice. Eventually, you should be able to get to this point where you can kind of balance an equation just by looking at it. You look at it and say, okay, there's more sulfur on this side than this side. I need to do this over here. But before we get to that point, we're actually going to introduce something else. And that something else is a process that we use to kind of help keep things straight while we're trying to learn the process of balancing chemical equations. That process is something called the atom economy method. Now, the atom economy method is just a note-keeping device. What we're going to start with is a chemical equation. Reactions on one side, products on the other. We're going to draw a line between the two, and we're basically just going to do some bookkeeping. There are this many carbons on each side. There are this many hydrogens on each side. There are this many sulfurs on each side. And we're going to use that to try to help us keep straight where we are. Okay, carbon's already balanced. Let's not touch carbon right now, if we can. Let's focus on the oxygen. It's the only thing that's not balanced. That's the whole point of the bookkeeping kind of method. As we make changes, that's going to change our bookkeeping. So I put a coefficient in front of carbon dioxide, and now I have to apply that coefficient to the count for my carbons and the count for my oxygen, since that compound had both in it. And so I just keep track of everything as I go until I get to the point where both sides of the equation are equal. I've got equal numbers of atoms of each kind of element on both sides of the equation. That's when I know it's balanced. Now, for those of you that have some experience with balancing chemical equations, you may not need this bookkeeping kind of methodology. That's when we transfer from bookkeeping to what they call balancing by inspection, where you just kind of look at it and go, okay, I need this and I need that. But until you're at that point where you have that level of comfort, this is a good crutch to kind of fall back on. Because again, it gives you the whole layout. You can see exactly how many elements are on each side. Now, some ways to make this easier for ourselves. One thing we can look for are ionic clusters. Try to keep them together. This is particularly true in replacement reactions. So in those replacement reactions where we had a nitrate on each side, or a sulfate on each side, or a carbonate on each side, you can keep that cluster of atoms together, which makes it a lot easier to count them than having to count out each individual element in the cluster. And so it's actually for this reason that replacement reactions are the easiest to batch. Because usually when we get to replacement reactions, after we do our atom economy, it's pretty easy to see what needs to be balanced and what is already balanced. We just make a small adjustment accordingly. Second thing, we need to look for compounds that have multiple subscripts. Usually we can use those subscripts to talk about the coefficients on the other side of the equation. Those subscripts usually help us define what those coefficients are. And that makes the balancing process easier because we already know, okay, I got a 4 and a 3 in this compound. Well, the carbon had 4, so I'm going to put a coefficient of 4 on the carbon compound. And the iron compound had a 3 on it, so I'm going to put the coefficient of 3 on the iron compound on the other side. If I use that as a starting point, that usually helps get me unstuck, at least initially. Finally, if an element is in multiple compounds and oxygen is always the most guilty of it, or at least is most of the time, save that one for last. Hopefully, by the time you balance out everything else, the answer for what you need to do with the oxygen is easy to see. Combustion reactions are the most guilty of that one. Because you'll have oxygen as a reactant, oxygen in multiple products, get everything else balanced out first. Come back to the oxygen last. It'll be pretty easy to see what you need to do from there. So let's look at a couple of examples. So here I have an example of an iron oxide compound reacting with hydrogen to make iron and water. First question I have for you. What kind of chemical reaction is this? Of those 5 types that we discussed, which one is this, Kristen? It is single replacement. How do you know? That's exactly right. Remember, in replacement reactions, we are looking for switching of places, basically. We had elemental hydrogen kicking out the iron to make elemental iron. And the reason we know this is a single replacement is because there's only one compound on each side. So with double replacement, there'd be 2 compounds on each side. That's what makes it double. So we start our atom economy up here, and we see that we have 3 irons, 4 oxygens, and 2 hydrogens here on the reactant side, 1 iron, 1 oxygen, and 2 hydrogens on the product side. Right now, other than hydrogen, nothing is balanced out. Now here's where we take those tips and tricks with us. Remember, one of those tips was about multiple subscripted compounds. Well, this would qualify as a multiple subscript compound. I've got in the iron compound, in the reactants, I've got 3 irons and 4 oxygens. That's where I'm going to start. And what we do, that subscript is going to come over and become the coefficient in front of the compound that contains that element. So the 3 irons become 3 irons. The 4 oxygens become 4 water, because each water has 1 oxygen in it. So as I make those changes, that's going to change my product side of the reaction. Then need 3 irons now, and 4 times 1 is 4 oxygen. But in the process, I also adjusted the hydrogen as well. 4 times 2 means I have 8 hydrogens now. So I've taken care of the iron problem. I've taken care of the oxygen problem. I've created a new problem with the hydrogen. But since hydrogen's by itself now, 8 divided by 2 tells me I need 4 hydrogen atoms, or hydrogen molecules, to give me 8 hydrogen atoms in total. So that's kind of always the last step. The last step is always going to be some kind of backtracking where I end up needing to rebalance something on the other side. But when you see compounds like this that have those multiple subscripts, that's a blessing. Because that means that the balancing has a lot less guesswork in it than it could normally. Any questions with this example? All right, let's look at another one. Here I've got a reaction between butane and oxygen to make carbon dioxide and water. First, what kind of reaction is this? Yes, this is a combustion reaction. We have oxygen as a reactant. We've got multiple oxide products. Combustion is the right answer there. So if we start up our atom economy, we see I've got 4 carbons, I've got 10 hydrogens, I've got 2 oxygens. On the flip side, I've got a carbon and CO2, 2 hydrogens and water, and a total of 3 oxygens. 2 from the carbon dioxide, 1 from the oxygen in water. So because there is oxygen in multiple products, this is what I kind of warned you about with combustion. Oxygen is going to be the thing we address the last. We're going to do a backtracking, basically. Start with carbon and hydrogen, see how that affects the oxygen, go back to the oxygen, and see where that takes us at the end. The other thing that we have going for us, again, we've got a multiple subscript compound here in butane. And we're going to use that to our full advantage. So I need 4 carbon dioxide to give me 4 carbon atoms. How many waters do I need to give me 10 hydrogens? 5. Okay, so this is where it can be a little bit tricky there. We're not going to move the 10 over. We're using the 10 to influence what the coefficient is on the other side. So my 4 carbon dioxides, I end up with 4 carbons and 8 oxygens. My 5 waters, I end up with 10 hydrogens and 5 oxygens. So my total number of oxygens now is 13. Everything's balanced except for the oxygen. Now, how many oxygen molecules do I need to give me 13 oxygen atoms? This one's not so easy. It's 13 divided by 2. 6.5. How do I get half of the molecule? Yeah. Okay, so when that situation comes up, what we're going to do is this. We're going to keep that, and we're actually just going to keep it in fractional form, 13 over 2 here. Now, obviously, there's no such thing as a half of a molecule. So to get rid of the half, we are going to multiply the whole thing by 2. Because 2 times a half gets rid of the half. So our final balanced chemical equation would be 2 butane, 2 times 13 in halves is 13 oxygen. 2 times 4 is 8 carbon dioxide. 2 times 5 is 10 water. Now we can double check our math, make sure that we get it right. Redo our numbers here. 2 times 4 is 8 carbons. 2 times 10 is 20 hydrogens. 13 times 2 is 26 oxygen. So that's my new reactant side of the equation. On the product side, I have 8 carbons and 16 oxygens. And I have 10 times 2 for 20 hydrogens and 10 times 1 for 10 oxygen. 16 plus 10 gives me 26 oxygens in total. So that kind of manipulation is possible. Happens most often with combustion reactions. Sometimes can happen with replacement reactions or combinations or something along those lines. What you do, it's okay to put a decimal in that spot or to keep it as a fraction. Let's understand that to actually interpret it correctly, you're going to need to multiply by the denominator of that fraction. That fraction is almost always going to be 1/2. So you just need to multiply by 2. Any questions with this one? All right, let's look at a third example here. We've got potassium sulfate reacting with barium chloride to make potassium chloride and barium sulfate. What kind of reaction is this? It is double replacement. Again, we're looking for things switching places. So you can see that the potassium and the barium have swapped partners here. The reason it's double replacement, you've got 2 compounds on each side. There's no element left by itself. Now, as I mentioned before, replacement reactions tend to be the easiest to balance. And if we get to our atom economy here, we can see why. Right now, I can look and see, okay, sulfate. So again, this is where the clustering can be really helpful. Recognizing that sulfate is on both sides of the reaction, I can keep it together as a single cluster rather than monitoring sulfur and oxygen. This is really important because we know that oxygen can exist in multiple compounds. And so it doesn't apply necessarily in this case, but it could in other cases where we see that I got multiple oxygen containing substances. Keeping the clusters together helps it keep it organized, makes it a little bit easier. But if I look, sulfates are balanced, bariums are balanced. The only thing that isn't balanced is the potassium and the chlorine. Both are unbalanced by the same amount, and both happen to be in the same spot. So with a simple modification, I put a 2 in front of potassium chloride. That balances the equation with just that one move. Like I said, you get a replacement reaction, usually pretty easy to balance, especially if they have polyatomic ions in them. With those clusters, make it a lot easier to keep track of everything. Right, questions with this one? All right, let's look at another. Here's another double replacement reaction. Toughest part about this one is just remembering that this subscript of 2 outside the parentheses means that there are 2 of these nitrate ions, 2 of these NO3s. But if we keep it all clustered together, the CO3s together and the NO3s together, instead of separating them out, this becomes a lot easier to do. Once again, you can see carbonates and magnesium are balanced. The only ones that are out of balance are the sodium and the nitrate, which happen to be in the same compound. So putting a coefficient of 2 in front to balance out them both. just by contrast, you see why the clustering actually works out really well here. Because if you didn't do that, let's just think back to the state of argument that we kept everything separated out. So if we had done that and turned this, okay, this is going to be carbon, oxygen, and nitrogen. Then I'd have one of these, and I'd have 9 of these, and 2 of these. I'd have 1, 6, 1. This isn't nearly as clear about what you need to do. I mean, yes, you fix the sodium problem, the other one just happens to work out as well. But it's a whole lot more complicated, and there's a lot more math involved to get there. So when I say clustering really does make a difference, it does. It makes a big difference in terms of what you're able to do and how quickly you are able to do it. So I've got one more thing that I want you to do. You can get started on this now, but we only got about 2 minutes left. So I'm actually gonna go ahead and just copy these down. Bring these with you when we come in on Wednesday. We'll start Wednesday just kind of going through this, making sure that you've kind of got the idea down before we move on to the next concept. And what we're getting to here eventually, what we're getting here to is with this idea of chemical equations and kind of the essence of chemical reactions in place, we're going to look at the most common and dangerous reaction of all, the combustion reaction. And so we're going to talk about, how things burn, why they burn, what affects how quickly a reaction proceeds, how to evaluate the dangers of those reactions. And the next 2 days are going to be about the combustion process and about how to put out those fires that start. So we'll be learning about all the different types of fire extinguishers and fire extinguishing equipment. That closes out chapter 5 for us. So if you've got that copy down, again, just bring that with you on Wednesday. We'll start there. But if you've got it down, you're free to go. Have a good day. All right, so here are the answers for this one. We're going to utilize our fish. So 5 carbon dioxide and 6 water. That means we need 16 oxygen. So things goes right there. So this one's similar to this. We'll use the subscript here. That's actually going to help us. Oxygen. With the other side of the script that we're going to do. So we're going to have 2 nitrogen over here. Similar process in number 3. We've got double subscript numbers. 2 goals rather. 2 X's to give us 3 sulfurs. We'll need 3 hydrogens to balance that out. And then finally, this last one. The thing that actually just pays attention to it phosphorus is already bound. So we're going to use chlorine here, and chlorine. That would be 3 chlorines and not 2 hydrogens, but you better do it. 2 hydrogens